before I go back to SP1. So I want to touch on this Reynolds number because it seems such an important parameter, and it is. In fluid mechanics, Reynolds number is used many, many times that describe essentially the effect due to viscosity. So I want to just take a moment to give you for the first time what it actually physically represents. It turns out if we work out the full equation of motion for viscous fluid, which we will do at the very last 2 weeks of the semester, resulting in the equation of motion including viscous effect. And then you find out in doing that, the Reynolds number will also appear in that equation. And when you compare the physics of what that viscosity in the denominator represents, it actually relates directly, not surprisingly, to the viscous forces. What is not clear is what we meant by rho v length scale and what I call an inertia effect. So what is the inertia effect? Inertia is resulting due to F equal to ma. The best way to describe that is if I'm traveling in a car at 60 miles per hour and I slam on the brake real hard, what will your body do? Lean forward. That's inertia. That's the body inertia just not being able to decelerate as fast. Right? So I want to set the stage here so that later on when we talk about viscous effect, boundary layer, which we have a dream of what it is, the Reynolds number allows us to have a mental picture of these two completing effects. When the Reynolds number is very small, and where have you seen that? In the pipe flow? You know, I draw you this diagram of the Moody. Anyone remember what the laminar flow is? Laminar. And that has to have a Reynolds number of what? Approximately value? Very good. It's about 2,000. So when the Reynolds number is small, it represents some type of flow behavior. In the pipe flow is laminar. When the Reynolds number is huge, meters, 10 meters, 100 meters, like the water that cuts through a submarine or aircraft carrier, that Reynolds number in the range of meters as opposed to 1,000 will allow me as a fluid mechanicist to picture what the flow is doing. That will be forthcoming when we get to subsequent discussion. So inertia effect is just deceleration, just as a simple mental exercise of what it really meant. Same with the car turning at the sharp corner, right? Your body will try to lean outward, and that's inertia effect. After the MA, your body cannot follow that sharp turn, and you try to go outward, just the same way that is due to a deceleration. So we'll come back to this after we set this initial stage. So problem 12 of chapter 7 is a totally new problem, and there are actually not many of those in fluid mechanics. They involve a pump, a water pump, that consists of a rotating impeller. Omega is rotational speed in RPM. And the pump works where water or fluid going from U towards perpendicularly to the impeller, and it go out in one direction. In going through the impeller, the pressure will rise significantly, and you find that in the power plant where you go from the condensed water to a very high pressure water to go back to the boiler. You're learning that in your thermodynamic right now. But for fluid, what we were told, the intuition part has been done for you for the problem, from the problem statement. You were told that the amount of pressure rise from this pump, pressure rise because work is being done on the fluid. is solely a function of 4 independent variables. The size, diameter, the type of fluid in terms of the density, how fast it's spinning, and someone remind me what's the Q? What does the nomenclature Q stand for? Volume flow rate. So I want you to stop and look at it from 30,000 feet down and tell me based on the problem statement, which is pressure-wise is a function only of density and then diameter, rotational speed, and Q. What had the problem assumed? What is one very important term that doesn't appear on the right-hand side because of our assumption? We assume it's invisible because the viscosity doesn't appear on my right-hand side. So it's a simplified dimensional analysis, just to make the problem more trackable. Okay? So I want you to be aware of that. Yes?
If you have your diameter, why do you need volumetric flow rate and not just velocity coming out?
Okay, velocity. So instead of Q, you're suggesting why don't I replace that with some kind of velocity? It will come. That's part of the problem. My answer to your question is they are related. They are related, and I'm going to show you somewhat loosely how, but not doing the problem for you. Fair question, but it turns out now I have some term that's very unconventional for us as a mechanical engineer. So I want to point you in some direction so that you don't fumble. First, what is the unit of RPM? Revolution per minute, the unit? It's 1 over time. Radian or 2 pi radian for 1 rotation has no unit. So make sure you don't make that mistake. If you cannot get the fundamental unit, you cannot get the right answer. I now need to decide what 3 dimensionally independent term I want to use to find the pi term. There are 4 on the right-hand side. So let me list you the 2 choices, and this is a very tricky question. Some of you may or may not see it. Those are my only 2 choices. Maybe I write it better so you can see the difference. Both cases, I choose the diameter and the RPM. Choice 1, I pick the density. Choice 2, I pick the volume flow rate. One of them is acceptable, the other one is not. First, tell me what is the criteria that dictate which 3 I pick. They have to be what? They have to be dimensionally independent. Dimensionally independent. So think very carefully. And if I go further, I will give you the answer for the homework. Are these 3 dimensionally independent? In another word, can I combine any 2 of them, raise to any power I wish, and get the same unit as the 3rd term? The answer is yes. This is not acceptable. It's not dimensionally independent. How? That's your homework. You prove to me how. So I have done half the problem for you by telling you what to choose. Without that, you may struggle. Furthermore, a comment was made about velocity. Fair enough. The unit I choose in here, or with the parameter I choose in here, diameter, omega, and density, can I combine two of these, and get the same unit as velocity? Which two? Don't tell me. Yeah,
The diameter is the diameter of the pump, right? Not of like the pipe coming out.
that's correct. It's the size of that impeller, correct. Fair enough. Do you understand my hints? Do you understand my question? So we are not used to and accustomed to think in terms of omega. Revolution per minute is not something we use all the time. But velocity is. So if you want to do this problem by inspection, which I encourage you to, then you find a term that will have the same unit as velocity and work the problem that way. Everything will become transparent if you do that. Because once I have velocity, I can go back to the pipe flow, I can go back to my airfoil, same parameters. Okay? So that's the thinking that I want you to have in order to reduce the problem, to make it more doable. Questions? Yeah, with that, I think the problem becomes a 5-minute problem. Okay. So shifting gear to just touch on SP1 because we didn't have time to answer any question on that last time. Solutions poster, I know some of you have time to look at that since last lecture. It's very often some of you are not able to reduce the answer to a pure number, so let me make sure that is done. Part 1. What is the dimensionless coefficient of pressure between 0, which is away from the intake, to station 1, which is just entering that rectangular channel? What would you apply? Bernoulli. Bernoulli. What is the velocity? 0? Far away from the intake? It's approximately 0. And so the algebra, very simply, when you work on that, will give you the part, dimensionless part, pressure coefficient of -1 for part A. All right? Part B is a little tricky, but I hope the hints that I gave you allow you to use the propane momentum equation, which I will write out for you. So we know that Bernoulli is not to be used, and continuity based on the problem statement allow us to calculate the velocity at 2, which at same amount of injection into the station 1 and 2 as the fluid coming in on the left-hand side. So the velocity increased by a factor of 2 exiting station 2. So momentum equation applied to control wall between the porous wall consists of my exiting momentum flux, m dot 2, u2, at station 2. And then at station 1, that's very traditional, right? The trick is the remaining part. I call it the m dot prime, and at velocity in the x direction entering my control wall from the side. But you are told the porous wall is perfectly perpendicular to the main flow direction. What's this term? It's zero. It's zero. Do you see that? Any question on this one here? So the algebra, I'll let you work on it. But the answer, when you couple continuity with this momentum, is the pressure coefficient is -6 in the form of P2 minus P1 normalized by V1 squared, half rho V1 squared. So let me stop. This is perhaps the tricky part of the problem. Yes?
Just to clarify, it's zero because it comes in perpendicular.
That's exactly what we are referring to. Because why? The x momentum equation carry all the momentum flux in the direction of x, but as they enter, they are perfectly perpendicular to x, and hence they carry no x momentum whatsoever. So this part B had two implications. First one is, please don't use Bernoulli, the flow is turbulent. A lot of mixing, because you cannot follow a streamline. Number two, in the x direction, if there's no momentum in the x direction, then the momentum flux is zero. I have no contribution to the forces. Do you get it? Okay, the next part, and then I will stop at that, is simply confusing you by saying I'm adding small amount of heat into the flow, but not enough to change the density. Now energy is being added because of the heating. Can you still use Bernoulli? Yes. And no bearing on the Bernoulli usage whatsoever. So I would just simply follow the streamline along the center and bang. The conclusion is no change. No change in pressure because there's not enough heating to change the density. And Bernoulli say no pressure change. Do you get it? Questions? What about the last part? Do I have to go through that too? The last part, okay. The last part is also a little bit contrary to what we did in station 1 to 2. Yeah, that's the part. Maybe some of you get trapped. So from 3 to 4, the reverse process happened, meaning fluid is being withdrawn from the control volume perpendicular to the main flow. So at first sight, the temptation is to reuse momentum equation. Reverse of what we did in part B. The only problem is when you rewrite the momentum equation from 3 to 4, as the fluid now leave this dashed line, the control surface, okay? Does it have any x momentum associated with it? The answer is yes. It's only after I enter that porous wall that momentum is destroyed. But at the instant, at the moment that I leave my control surface, I still have, I call it Ux prime. I still have a finite x momentum with me. And that has to be accounted for, and it's not zero. It is something I don't know, because it's not enough information given in the problem statement for me to estimate. So the use of momentum will give you the wrong answer, because you have neglected a certain part of the x momentum in your formulation. And that's why in the hints, I asked you, besides the withdrawal of the fluid due to suction, can you still follow a center streamline that is almost undisturbed? And there's no turbulent mixing, so that Bernoulli can be used. And that's how you calculate the last pressure drop from 3 to 4. So it's a little bit tricky for the last part, how you were able to use Bernoulli where all 4 conditions are met. And yet you cannot use momentum for the reason I mentioned. Right? Question? On this one? Yes?
If you were maybe given like an anchoring force, could you then?
Now,
Yeah.
I choose the control volume internal to my wall. For that reason, because no anchoring force was mentioned or given to me. So I want to avoid having to deal with anchoring force. And by choosing the internal control volume, I succeeded in avoiding that. And that's a little tricky and not typical of the problem we have done in the past for homework. So that's a very good comment also. If you choose the control volume cutting through the wall, then the anchoring force will be present. There's no way of knowing what it is. Okay? So a little tricky from that standpoint and not traditional. But the main takeaway is the fact Bernoulli had nothing to do with energy, and under those 4 conditions, you can use it safely. All right, I'll cover the cavitation problem next time.